Welcome, everybody. So, the Flat Earth community, they have evolved. They've gone from being stupid on purpose and claiming that their ignorance is a virtue because all your fancy degrees just prove how indoctrinated you are, to pretending to know how science actually works. They've gotten sick of being laughed at, and so now they string together bits of nonsense while borrowing scientific ideas, while being incredibly condescending and claiming that you don't get it. Like this.
But you keep talking about gravity, invoking it. It proves the ball Earth, as she's saying. No, you look at the lights in the sky, you presuppose a distance, a certain mass, relative nature, then you presuppose a causal agent called space-time bending and warping and dilating, et cetera, et cetera. Actually, whenever we presuppose a theory of relativity, apply it to the universe, it's off by 95%. It's called dark matter and dark energy. Not only do you not know how to fully explain gravity, or have you ever proven it, it's not even mathematically viable yet. It's off by 95%. You should look into it. But McToon, here's my question for you. If everything is intrinsically electrostatic, and electrostatics is 10 to the 39th power stronger than gravity even claims to be, and all molecular and intermolecular electrostatic or attractive forces are electrostatic in nature, how is it that you isolated gravity and proved it to be the causal agent of...
Okay, I'm sorry that you had to hear that, but that's just an example of the kind of stupid word salad stuff that they are now throwing around. So they've never had an explanation for why anything happens. They've always just said nuh-uh to gravity, and they've moved on to electrostatics. Not too long ago, they claimed that the reason things fall and all that was density and buoyancy. And they actually still claim that. They claim that water sits below the air because of density, but also that electrostatics is what makes objects fall to the ground and accelerate. But density also makes objects fall. I don't really know, and it's pretty clear that neither do they. They don't have a working model, as we will demonstrate today. That is what we are doing today. The purpose of this video is to demonstrate that, no, flurfers, electrostatics is not the answer. So, what is electrostatics? Well, as the name implies, it's the branch of physics that deals with electric charges that are at rest and the forces between them. So here we can see a positively and a negatively charged object being attracted together. Not magnets. This is not magnetism. It's not electromagnetism. It's not electricity. It's electrostatics. We've all experienced the electrostatic force, like this kitten here has, but if you've done something as simple as just rubbed your feet on a rug, pulled a dryer sheet off your sweater, rubbed a balloon on your hair, or seen a Van de Graaff generator at some point in your life, you've experienced the electrostatic force. I will get into specifics as we go, but this is really all you need to know for now. An electrostatic force occurs when two objects have stored electric charge in them. It may have alike charges, if they have alike charges, then they'll repel each other. Two positives will repel, two negatives will repel, but opposites attract. Oh, my screen went black for a second. Thank you for the cowboy hat. So this is virtually always caused by excess electrons rubbing off onto the surface of something. So we can actually demonstrate that. I have a little video that I made here for you. So what you can do, this is called an electrophorus, and it might be kind of small, but if you squint, maybe you can see what's going on. So just take an insulator, in this case a foam plate, rub it with some wool or a microfiber cloth. That's going to build up electrons onto the surface. And then here's the actual device. So what I have is a conductor, an aluminum, like a pie pan or tin pan or whatever, and another insulator that's just a styrofoam cup, a straw, and then on the string there's a piece of an aluminum. So it's kind of hard to see, but they actually repel each other, and then if you touch it, they'll wiggle back and forth. And then if I touch it, that grounds it, and the electrostatic force is eliminated because I grounded it. Now if I pick it up, it resets. So as I bring my finger up, it wiggles back and forth, and the charges are alike, so it's repelling, but as soon as I touch it, it goes back to rest because all electrostatic potential has been removed. That's what happens when you ground something. and then we start all over again. So you can do that forever with an electrophorus, and you can make one for just a couple of bucks. So check it out sometime. Here's why electrostatics is not the answer, and it can't be the answer. This is the equation for electrostatics. So we have the electrostatic force, F, is equal to, there's a constant, it's called Coulomb's constant, or Coulomb's constant. You multiply that by what are called 2-point charges. So those are just the charges that two objects have. And then you divide everything by this. Now that right there is r squared. That's the radius. The electrostatic force pulls objects towards the center from all directions. There's not a single geometry that works for this other than a sphere, because only on a sphere are you equidistant from the center. That's why we have a radius here. So Earth is not a perfect sphere by any means, but the difference, that's Mount Everest. And if we zoom out, we can see the scale here. The difference between being on Mount Everest and being at sea level with respect to your distance to the center of Earth is 0.126%. Not enough difference to make any difference. The flat Earth version of electrostatics has no center. So here's an illustration of a flat Earth, for example. We can't say that the North Pole is the center, because if that were the case, then everything that falls, if electrostatics is what makes things fall, then everything would fall towards the North Pole. If I would drop something, it would move towards the North Pole. And the effect would actually be more extreme the farther away from the North Pole you are, because your angle towards the North Pole gets sharper and sharper, or we could say flatter, actually, as you move farther away from the North Pole. I'm guessing that they would say that the Earth overall has a charge that's spread over its entire surface, rather than the Earth, quote unquote, having a single charge. Now, I'll show you how that completely fails later on. But there are a lot more reasons why electrostatics isn't the answer, but I'll save some more specifics for the very next segment, which I have decided to title Dumb Things Dumb People Who Don't Know What Electrostatics Is Say. And this is trademarked, so you can't use it. All right. Thing number 1.
All I'm saying is everything's intrinsically electrostatic.
Oh, sorry. That kind of cut off there. But what he said is everything is intrinsically electrostatic, or everything has an electric charge. That is the first dumb thing that dumb people who don't know what electrostatics is say. Okay, well, why is this wrong? In the sense that an airtight metal box that is welded shut has wind in it because the air molecules are technically in motion, yes, you could say an airtight welded metal box has wind in it for that reason. But in the sense that there is a measurable difference in electric potential between all objects, then no, this claim that everything is intrinsically electrostatic, it may be true in a sense, but it fails to explain anything. In order for this claim to be true, and by true I mean be the actual reason why things fall and why things accelerate when they fall, then the person, or in order for the claim itself, in order for just the claim to be true, everything is intrinsically electrostatic, the person arguing only has to assume that any object, no matter how big or small, has one extra or one missing electron. That would be true. Just like if a single air molecule is moving in a airtight, welded shut metal box, it has wind in a sense. But in order for this claim here to support the idea that therefore this is the universal force that causes all objects to fall to Earth, you need to prove there is always a significant difference in electric potential between all heavier than air objects and the Earth. You'd also have to prove that the Earth has a constant charge, which is positive or negative. Now, absolutely none of that has ever been described or discovered whatsoever. It just simply isn't the case.
Static, and electrostatics is 10 to the 39th power stronger than gravity even claims to be. And all molecular and intermolecular electrostatic or attractive forces are electrostatic in nature. How is it that you isolated gravity and proved it to be the causal agent of something.
Well,
okay, so I think that was supposed to cut off earlier than it did. But the only part that's relevant here is electrostatics is 10 to the 39th power stronger than gravity. It's not. For a lot of reasons, this claim is just actually completely false. So what I think he meant there, and that guy's name is Whitsitt, if any of you don't know, but what he probably meant is it's true that the electrostatic force between two protons in an atomic nucleus is around 10 to the 36th, not 39th, 10 to the 36th times stronger than the gravitational force between them. But that's a terrible way to compare two forces. It makes like absolutely no sense. If you want to compare two forces, one thing you can do is you can look at the force constants in the equations. So for electrostatics, here it is. K is the force constant. It's Coulomb's constant. This is gravity over here. So the equations for gravity and electrostatics are actually, they're set up exactly the same. In gravity, we're dealing with mass. In electrostatics, we're dealing with electric potential. But we still have the radius, the distance between them, and all of that is multiplied by that constant. But anyways, getting back to the point, if we look at the gravitational constant, G, and compare that to the electrostatic constant, then what we find is the electrostatic constant is 1.35 times 10 to the 20th times stronger than the gravitational constant. So that is still obviously much stronger. It's more than a billion, but it's not 10 to the 39th power. But like the fact that a charged balloon sticks to the ceiling completely mummifies this talking point about all this. An electrostatic attraction, so this is what we're told to believe. An electrostatic attraction between Earth and all objects is what makes them fall, right? But a static electrically charged balloon doesn't do that, even though we know that it has a strong electrostatic charge to it. Even though the Earth would be the ultimate strongest electrostatic object, the balloon will stick to the ceiling. There's clearly more than one force at play here, and it can't just be electrostatics, or the balloon would go to the ground. Or if the balloon somehow had the opposite charge of Earth, then the balloon would rise up. But only helium balloons do that. Regular balloons don't do that if you rub your hair on them. So I want to congratulate Whitsitt. He is right. Electrostatics is stronger than gravity, which is exactly why the balloon sticks to the ceiling and exactly why everything else that's heavier than air falls. But another thing that completely destroys this stupid talking point is that Earth doesn't have an electrostatic charge. So I could therefore say gravity is 10 to the some sort of huge number times stronger than electrostatics. And it would be completely true in that case, right? Because this actually makes no sense at all, comparing the force this way. When you compare subatomic particles that do have an electrostatic charge, electrostatics is stronger. But when you compare large objects that aren't charged, like a block of lead, then gravity is stronger. So this claim is just dumb all the way around.
Big differential.
So the Earth have an electrostatic resonance?
A resonance?
A resonance field, yeah. Yes or no?
I don't even know what you mean by an electrostatic resonance field.
Okay, I'm sorry that you're
just making up crap.
Okay, so let me just all I'm saying is we can move on from this as a more technical aspect. It's actually not necessary, but all I'm saying is everything's intrinsically electrostatic.
Okay, so there's a lot to unpack there. Notice how he brought up the electrostatic resonance, and notice how he didn't unpack it or explain it at all. All he did was say, this is a more technical aspect, it's actually not super relevant. Then why bring it up? It was actually completely made up. I think maybe when I do debates, I think I'll do this from now on. I'll just be arguing with somebody and I'll say, have you ever heard of the extrapolated platypus diorama? And then I'm going to laugh and call them stupid for not knowing what it was, even though I made it up. So does Earth have an electrostatic resonance? Yes or no? No. There's no electrostatic resonance. And this has nothing to do with anything. Resonance is something that causes objects to vibrate. And a type of resonance like this couldn't make objects fall or do anything. It makes no sense. It has no ability to explain anything. And now we move on to our next section, which is titled Dumb Things Dumb People Who Don't Know What Electrostatics Is Don't Realize. It's also trademarked. It's slightly different, but it still works. So, in this debate, a lot of you probably know who McToon is. But McToon brought up these points, but the idiot just sort of gish-galloped away from the entire thing. For example, anything that is grounded would be weightless. If electrostatics is what makes objects fall to the ground, if it's the force that pulls them towards the earth, then so electrostatics only works if there's a difference in electric potential or stored electric charge. So if you ground something, that means that you have removed any difference in potential from that object and from the ground. And so there would be no force acting on it. Another thing is, and again, McToon brought this up, so credit to him, objects in Faraday cages should be completely weightless, as they are also shielded from outside electromagnetic and electrostatic forces. So you can be inside of a Faraday cage, and somebody can bring a huge amount of volts, hundreds of thousands of volts, close to you, and it cannot interact with you because the Faraday cage blocks any difference in potential. So there's nothing there. So if you just put something in a Faraday cage, it should also be weightless. And I don't need to tell you that that's not the case. You can see it for yourself. That chick is not floating. Another thing is anything that has the same charge as Earth should be inclined to float. And things with the same charge as Earth should, well, let me explain that before I move on. So any objects with the same charge, they would repel each other. So is this the explanation for why a helium balloon floats? Does helium have a certain electrostatic charge, and that charge is the same as Earth, and that's why they go up? We know for a fact that that's not the case. First of all, Earth just simply doesn't have a charge of any kind. In different parts of the Earth's surface, you can set up some weird things. Like there are people that can get like a weak current out of the Earth by setting up like nickel and maybe some galvanized metal and some copper. But Earth doesn't have a stored like unified charge over its surface, and helium certainly doesn't either. But the other thing is, if two objects have the same charge, and you try to bring them close together, what you find is the force between them gets stronger and stronger and stronger. So if you've ever played with like neodymium magnets and tried to push them together, it's extremely hard the closer you get. So what we would find on Earth is there would be objects. If electrostatics is what makes things fall, if that's what attracts certain things to the ground, that if we can find things that have the same charge as the Earth, they would be harder to push the closer they got to the ground. So this would be like if you took a helium balloon and it got harder and harder to push it down. Now, a flat earther could find a mime who could act that out, and it would be really funny. I would watch that. I would laugh, but it would obviously be totally fake. The other thing is, I feel like I already know what the response I don't know if there's any flat earthers watching this right now, but I already know exactly what they would say. They would say, nuh-uh, because density and buoyancy. Okay, so what we've done is we've explained, or I've given examples of how you could test this electrostatic claim, and they completely fall apart. Now, if you're going to say that's not fatal to my argument because of density and buoyancy, if there's zero difference between the way objects fall and their weight when we manipulate them in a way that we know removes the electrostatic force, then clearly the electrostatic force has zero bearing on the entire thing, on any of these things. Let me repeat that. It has zero bearing. So if you're ever talking to a flat earther, if they say something about electrostatics, and you can, any of these things I've said, or any of the things McToon said, or something you come up with, if you find out a way to test that claim and they say, no, it's density and buoyancy, then that means that the electrostatics isn't actually explaining anything whatsoever. But this does raise an interesting question. If it's not electrostatics, then what is it? Well, it's gravity. Duh. Now, a flat earther will say something like, you've never proven gravity. It's all just based on assumptions. You can't isolate it or anything like that. I'm going to go over in detail how we can actually prove that Earth is a sphere. We are going to use gravity, but what we're first going to do is experimentally prove that Earth is a sphere, and then look at the equation for gravity and see how, unlike electrostatics, it doesn't fail catastrophically at everything. So this is actually going to be really technical and really detailed, so buckle in. One thing is that, well, I can just leave this here. We know the radius of Earth, and we've known it for thousands of years, but we don't have to just rely on Eratosthenes. We can test this ourselves. In fact, any of you could do this, because I did this just sitting at home. And you probably can't see this very well, but I got all my data from this website called, I'll make this a little bit bigger. It's called sunearthtools.com. You can get data about the position of the sun with it. Cayambe in Ecuador is right on the equator. So on the equinox, what we find is the sun rises to 0.0036 degrees, which is, we're just going to call that 0. Now we could also call it 90 because it's right above us, but depending on the frame of reference, whatever, 0 is basically the same thing as 90. And that makes perfect sense because it's on the equator, and this is during the equinox. So in another place that's far away from the equator, where I used to live actually, Watertown, South Dakota, the sun rises on the equator on the exact same day. The sun rises to 45.45 degrees. The straight line distance between these places from Watertown and the equator is 4,973.76 kilometers. So I have that on the bottom there. I picked Cayambe because if you just go straight south from Watertown down to the equator, you end up in the Pacific Ocean, and the Pacific Ocean isn't really a place. So I wanted to pick a spot that was on the equator, but it doesn't really matter. Okay. If Earth is flat, we can do some very basic trigonometry, which you see right here. And what we can do is we'll put 4,973.76 as our base and an angle of 90 degrees. And we can figure out that the sun, according to the flat Earth model, the sun is 5,053 kilometers away. This is basic trigonometry, like freshman, sophomore level stuff. Okay, this, I don't see how you could possibly disagree with this. Those are the numbers. There it is. We're just going to put this into our pocket for now, the 5,053 kilometers. That's how far away the sun is. We're going to use that to make predictions, because that's how science really works. And we're going to see that the flat Earth model completely fails to make any predictions. But instead, let's do this. Let's calculate the circumference of Earth using this. This is how the Eratosthenes experiment works. And you could do this whenever you want, from a location that you pick. So what we can do is we're going to assume that the Earth is a sphere. So a sphere would have 360 degrees, right? Well, take 360 divided by 45.45, because that was that's basically our angle. It's our latitude for where Watertown was. Well, actually, sorry, that's not the latitude. That is the angle that the sun makes. We'll come back to this in a little bit. Multiply that by the distance to the equator from where we were. And then what we get is, the number we get with that is 39,396 kilometers, which is less than a 2% error of the accepted value, which is 40,075 kilometers. Now, another important thing we're going to do here, and we're just going to put this in our pocket for now, we're going to divide that by 2 pi to figure out the radius of Earth. So the radius of Earth, assuming that Earth is a sphere, again, we're making assumptions and we're doing some maths right now, but we're going to use this to make predictions. Again, flurfers, they'll say stupid stuff like, you're just assuming, blah, 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 it's confirmation bias. Nope. Doing experiments and making predictions is not confirmation bias. It's the exact opposite of that. We are testing our claim. So with a radius of 6,371 kilometers, we will come back to that later. Now what we're going to do is prove that the Earth isn't flat using this geometry stuff, okay? So if we go to Houston, Texas, we'll pick a different place. Houston is 3,294 kilometers from the equator. So we have an unknown. We're going to predict what the angle the sun will make is, right? So if we assume Earth is flat, we already know how far away the sun is. It was 5,053 kilometers. We did the trigonometry for that earlier. So this means we can calculate exactly how high the sun will appear in the sky from Houston on the equinox. And the answer is, or the prediction on the flat Earth model is, the sun will rise to 56.9 degrees. So that's what flat Earth science, or in other words, stupid science, tells us. The actual answer is, on the equinox, the sun rises to 61 degrees. So earlier, when we used our globe model, we did have, a small error, but it was less than 2%. We are close to a 7% error now. So this is a problem. But let's pick a different city. Let's pick Anchorage, Alaska. So Anchorage is much farther away. It's 6,791 kilometers from the Earth, from the equator. If we assume that the sun is the distance it is, which we calculated that, what we would predict is, you can kind of see the number right here, the sun should rise to 36.65 degrees above the horizon. That's what flat Earth science, otherwise known as stupid science, tells us. The problem is it actually rises to only 29.2 degrees. So now our error is much, much, much larger. It's 25.5%. Well, the problem is, as you might have guessed it is, the Earth is not flat, right? That's why the flat Earth model can't predict anything, but the globe model perfectly predicts all of these things. On a sphere with a sun 150 million kilometers away, what you get is the light we get from the sun is parallel to the Earth because of how far away the sun is. So wherever you are, what I did here is I put a vertical marker on 45 degrees latitude. So that is halfway from the equator to the North Pole. Now, from your perspective, horizon is just this tangent line that extends out in all directions. So what that would mean is the sun is going to rise to an angle that exactly matches your latitude. You have to kind of draw out the model like this, but it's really simple geometry. That's what happens, and that's exactly what we find all over the planet. So for example, in Anchorage, Alaska, the flat Earth model got this completely wrong. It predicted that it would rise to about 37 degrees. It's actually 29 degrees. So if we go to Anchorage and we look at its latitude, now here's where it's actually kind of weird. We have to flip this. We call the equator 0 degrees and the North Pole 90 degrees. But for this, if we're standing on the surface here, then actually extending out from the equator is 90 and the North Pole is 0. But we have 61.2 degrees. Well, what's 61 minus 90? It's 29. What is the angle that is predicted? 29 degrees. Now, they're not perfect. They can be off by, it's usually less than 1 degree. But I don't have to tell you that being off by 1 degree is much better than the 25% error we got with the flat Earth model. So there we go. This is how we can prove that the Earth is a ball and that it can't possibly be a sphere. All right, what is next? Oh, So that was kind of a tangent, but it was important to prove that the Earth can't possibly be flat using that. And that's a very simple way to do it. Earlier, though, we calculated the radius of Earth. Now, that's an extremely important part of this equation here. This is the electrostatic equation down here, but this is gravity. Notice how they're set up the same way. We talked about that earlier. So this radius problem is one of the biggest reasons why the electrostatics hypothesis completely fails at everything. We know, so if we take the gravity equation, we can rearrange that and solve for different things, such as the mass of the Earth. And it's actually not that hard to do. We know the acceleration of gravity. We've known that for centuries. So that's what Fg would be in this equation over here. So replace that with 9.8 meters per second squared. We've known the universal gravitational constant for centuries too. Henry Cavendish figured that out. That's big G. So by doing this, if we rearrange the equation, we can solve for the mass of our planet. So our planet has a mass of, if we just round this up a tiny bit, 6 times 10 to the 24th kilograms. Now, and we know the radius. So here's why that's important. Well, first of all, we kind of already talked about this, but so like an idiot, flat earthers, that's you, they might say something like, these are all assumptions. You're just proving what you assumed was true. This is circular reasoning, blah, 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 blah. No, the equations, this right here, these exist only to test our claims. We did that earlier. We used the math and then we made multiple predictions. So, but in this case, for example, if the Earth is a giant sphere, sorry, let me go to the next picture. If the Earth is a giant sphere, then the force of gravity, which is just the rate at which things fall, that should be unnoticeably different, whether you've dropped something from a 10-foot ladder or the tallest building in the world. Now, that's a little hard to test, but it has been done. Alternatively, you could just check your weight. This is also an extremely easy way of doing this. If gravity is the thing pulling you down, and the strength of gravity depends on how far away you are from the center, then your weight also should be not at all noticeably different between being on top of Mount Everest or just being in Death Valley, which is literally below sea level. To do that, your weight is just your mass in kilograms multiplied by the acceleration of gravity. So if the force of gravity, which is acceleration, does depend on your distance between you and the center of the object, and the center of Earth is many thousands of kilometers away, then your weight should be virtually identical in these places. Now, if you have a sensitive enough scale, you can test this. It has been tested, and then we know this for a fact. I don't remember what this is called, but there's actually there's a group that takes this little gnome here, and they have a really sensitive scale, and they do this. They test the weight of the gnome on like the bottom of buildings and then the top of buildings, and there is a change in the weight, but it's extremely microscopic. It's like 0.00 something ounces or grams. It's very, very, very small. With the electrostatic claim, here's why this fails totally. They might assume that the whole ground is charged. There isn't one single like point charge. It's that there's a charge spread over the entire Earth. But if that was true, then, well, for example, there's so many problems with this. How far down does the flat Earth go? Where does the charge start? See, these are the kinds of things that need to be answered so they can be tested to see if the claim actually makes any sense. Because if we know it, then we can plug in the charges and the radius squared and see if there's any noticeable difference. So, for example, if you're on top of a mountain, your weight should be noticeably different because the flat earthers are not telling us that many, many thousands of kilometers below ground is where this giant electrostatic potential is stored, but that it's stored like equally out in all directions in a two-dimensional disk that then rises above us or anything like that. What we've done here is we've used real science. We took mathematical formulas developed to empirically test a series of predictions. The predictions were accurate, which means assuming gravity and a spherical Earth, we have a correct model. So in other words, it's not electrostatics, bro.